Hello, student. Welcome to this chapter, Lattice Dynamics. And now, in this class, I am going to explain the wave motion in a linear chain of diatomic lattice. So, in the picture or in this diagram, you are looking at the diatomic lattice because these are the two kinds of atoms. This is atom of one kind, and this is the another, and they are placed alternatively. This 2n is the numbering for this atom. The atom which is designated as 2n is having the mass m2, and the atom which is designated as 2n plus 1 is having the mass m1. Like this it continues. So a is the distance between two atoms, consecutive atoms. It is like the lattice parameter, as it is the distance between two successive atoms. It is like a lattice parameter, and here this represents the distance between these two atoms. And when this chain of linear chain of diatomic lattice is excited, these atoms, let us say at one instant of time, these atoms are displaced to the right in this way. So therefore, this x2n plus 1 is the displacement of this atom to an atom to this position, and this x2n plus 1 is the displacement of this atom to which is at the atom 2n plus 1 to this position. So in this way, all the atoms gets displaced through some distance. So this is what happens in case of the diatomic lattice. So So I'm considering a linear chain of diatomic lattice, such as the lattice of the sodium chloride or the cesium chloride. And the atoms are arranged in such a way that the even numbers have a mass m2, and odd numbers have the mass m1. The distance between the nearest neighbors is a, and that of the next neighbors is 2a, because they are equally spaced. So therefore it is 2a plus a, it becomes 2a. And and now we consider only waves which propagate in symmetry directions, such as 111 in case of sodium chloride, or 110 in case of cesium chloride, for which a single plane contains only a single type of atoms. So for symmetry considerations, I am considering only the symmetry directions, 111 and 110. So that means when you are in this 110 direction, that plane will contains only one kind of atoms. Let us say, suppose if you are referring to the sodium chloride, you will have only either sodium atoms or chlorine atoms. That's the meaning. So we assume that the only forces between nearest neighbors are important and are obeying the Hooke's law within the. That means we are in the within the elastic limit, and hence the vibrations are harmonic in nature. So that means what is the meaning of nearest neighbors is like this. Suppose I am considering this atom, which is which is designated as a 2n. The nearest neighbor to this atom is this one, which is designated as 2n plus 1 atom, and also 2n minus 1 atom. So these two are the nearest neighbors. Next nearest neighbors means this atom. 2n plus 2 atom becomes the next nearest atoms. So for simplicity, we are considering the interactions between only the nearest neighbors, which is of more important. So I am coming back to this, and here the interatomic forces acting on the atom 2n are given by this equation. F1 is equal to beta into x2 x2n minus 1 minus x2n minus beta into x2n minus x2n minus 1. How this equation is written? This equation is written simply based on Hooke's law. Hooke's law, F is equal to minus kx, where F is the force and k is the force constant and x is the displacement. And this negative sign indicates that the displacement is opposite to that of the applied force. That is the Hooke's law equation. So based on that, that equation is written. And actually, two forces are there. Two forces are acting on the atom 2n. I will show in this diagram. So this is the 2n atom. One force acts between 2n atom and 2n plus 1 atom. Let us say this is to the left, and another force is acting between 2n minus 1 atom and 2n atom, and that is to the right. So these are the two forces acting on the atom 2n, and since they are opposite to each other, we are subtracting one force from the another. So negative sign comes this because of this reason, and this equation is simplified and it becomes f1 is equal to beta into x2n plus 1 plus x2n minus 1 minus x2 minus 2x2n. So just simplify this, you will get this equation. Similarly, the interatomic forces acting on the atom 2n plus 1 are given by this equation as I explained just now. 2n plus 1 is to the next of 2n atom, and similarly two forces are acting on this 2n plus 1 atom and which are opposite in direction. So therefore we are subtracting here, and again you simplify this equation, you will get this equation. So this is equation 2. And now using Newton's second law of motion, equations 1 and 2 can be written as this way. So here F1 is there actually. This F1 is written as m2 into d square x2n divided by dt square. As you know that uh, Newton's second law means F is equal to ma, mass into acceleration. So here m is mass of that atom, and this is the acceleration of that particle, that atom. So f1 is replaced with this thing, and LHS is as it is. Similarly, in another equation 2, we are replacing f2 with m1 into d square x2n plus 1 divided by dt square. And this is also in Newton's second law form, and RHS is written as it is. Since m1 mass of the atom, one atom, that is m1 is not equal to another atom m2. So the respective amplitudes of waves 3 and 4 are not equal because of this reason, and let the eta and zeta are the amplitudes of waves 3 and 4 respectively. We look for the solutions of these two waves of the form x2n is equal to eta into e to the power I into omega t minus 2kNA, where the terms have their usual meaning. And another equation 4 is written in this way. The solutions for equation 4 are x 2n plus 1 is equal to zeta into e to the power I omega t minus 2n plus 1 into k. So in this way, we got the equations 5 and 6. We have to differentiate equations 5 and 6 twice with respect to time. We get this thing d square x2 under dt square is equal to minus omega square eta into e to the power I omega t minus 2n ka. When we differentiate first time, it becomes I omega into that quantity, and when we differentiate second time, another I omega comes. So therefore I square omega square is multiplied by this term, and I square becomes minus 1, and this omega square is written there. So because of that reason, this minus n comes. That is I square. I square is equal to minus 1. Similarly, equation 6 is also differentiated and simplified, and we are getting in this way. Again, from equations 5 and 6, we can write x2n plus 2 is equal to eta into e to the power I omega t minus 2n plus 2 into ke. How it is written? Just n is replaced with 2n plus 2. This equation is written, and here two terms are there. So one term is separated. That leads that is completely x2n. So that x2n represents this one. So this part. So this part is separated from that equation, and remaining left is this much, that is e to the power minus 2 ik. You can work out again, you will come to, you will get this thing. So it's very simple. And similarly, x 2n minus 1 is equal to zeta into e to the power I omega t minus 2n minus 1 into ka. That means wherever n is there is just 2n minus 1 is written, and here is this term is separated from this term, and it is multiplied by e to the power 2 ika. So this is equations 9 and 10. And now substitute the equations 5, 6, 7, 8, 9 and 10 into equation 3 and 4, and we get like this. M2 d square x2 divided by dt square was there. In place of that, its value is substituted, and similarly all the values in equation 3 and 4 are substituted using these equations 5, 6, 7, 8, 9 and 10. So similarly that equation 4, in the equation 4 also we substitute all the values, they come like this. And simplifying equations we get, so actually we have to cancel this term, and this e raised to I omega t minus 2 and k is there. This is completely cancelled here. Here also that term is there, and here also that term is there, and here this term is completely gone. And similarly in this equation also this term is cancelled from here, and here. So you simplify that one, you will get these two equations. So these are the two equations obtained after simplification of about two equations. And now here next here this equation is written in this way. This minus 2 beta into eta is taken to the LHS, and this e raised to ika plus e raised to minus ika, as per trigonometry it is 2 cos ka, that is also written. And similarly this equation, that is minus 2 beta xi, is taken to LHS, and this thing is written as a 2 cos ka. So we obtain these two equations. And next you take that RHS part to the LHS, it becomes equal to 0, and here also it becomes 0. So the equations 11 and 12 have a non-trivial solution only if the determinant of the coefficients of zeta and eta vanishes. So this is the coefficient of eta, and this is the coefficient of zeta. So the determinant of that coefficients of zeta and eta should vanish for a non-trivial solution. So this is the determinant we have written. It is the coefficients of simply zeta and eta. So we have to solve this determinant for its modulus value of, or for its magnitude value. So how it is solved, you know, it is very simple. Just take the cross multiplication. This term is multiplied with this term minus this term is multiplied with this term. Then it is simplified. So it is done here. This is the multiplication and subtraction is equal to 0. That means I am determining the modulus or magnitude of that determinant. So multiply this and you will get all these things equations, and rearrange the terms in this way. And then you divide the whole this equation by m1 m2, so that this equation is converting into like this. So it is 2 beta into m1 plus m2 divided by m1 a2. So here this completely goes cancelled. So just we are dividing this equation with the m1 m2. This is the result. So this is a quadratic equation in omega square, because the quadratic equation is that is ax square plus bx plus c is equal to 0 is called as the quadratic equation. So similarly, this is in quadratic form. As you know, the quadratic equation is having two solutions. The two solutions of this quadratic equations are omega plus or minus square is equal to, as you know, the formula for quadratic equation is minus b plus or minus root of b square minus 4ac whole divided by 2a. So that is the formula used to get the solution of a quadratic equation. Same formula is used here, and a in place of a1 is there, and in place of b this the whole term is there, and in place of c this whole term is there. So all these terms are used and written in or substituted into that formula, that is uh, b square plus or minus root of b, sorry, minus b plus or minus root of b square minus 4ac divided by 2a. So that is the formula. Using that formula, we have written this one. It's very simple. So in this way, so this m1 plus m2 divided by m1 m2 can be written in this way. Sometimes in some books they have written in this way. So this is referred as the very important relation called as the dispersion relation for a diatomic lattice, because it connects omega and k. So therefore, this is called as a dispersion relation. So thus there are as this is omega plus or minus is there, that shows that there are two angular frequencies omega plus and omega minus corresponding to a single value of k. The figure shows the plot of omega versus k, or the dispersion relation for diatomic lattice is like this. So both the solutions, that is omega plus and omega minus, are plotted here. So this is one, and this is another. This is omega plus. This curve is for omega plus, and this curve is for omega minus. And this lower curve is referred to as the acoustical branch, and this is upper is referred as the optical branch. This is called as the acoustical branch because the vibrations which are present in this type of are just like the sound waves. So therefore, this is termed as the acoustic branch. And the vibrations which are present in this band are excited by any light energy or light source. So therefore, they are called as the optical branch. So this is the value of this point. This we are going to get it, and this is the value of this. This is the value of this point, and this is the value of this point. I will show you how we are going to get this one. And here in between forbidden frequency band is there. Suppose if the vibrations are having the frequencies in this range, they are not transmitted by the lattice. Because of that reason, it is called as the forbidden frequency band. So same thing is written here. So it is observed that there are two branches, one corresponding to omega minus and the other corresponding to omega plus, and these are called as acoustical branch and optical branch respectively. The omega minus branch is termed so because they represent long wavelength elastic waves whose frequency is independent of its velocity. They are like sound waves. And the omega plus branch is termed so because the frequency of this branch lies near the infrared region of the spectrum. Then the frequency range between the top of the acoustic branch and the bottom of the optical branch is forbidden, I have shown in the diagram, and the lattice cannot transmit such a wave. Therefore, waves in this region are strongly attenuated by the diatomic lattice, which behaves as a mechanical bandpass filter. The width of this band depends upon the mass ratio. If the mass ratio is unity, the band, the two branches meet each other and the forbidden band disappear. This case we are going to study in next sections. So first we'll work out for the optical branch. For the negative root, this corresponds to this corresponds to the acoustic branch at k is equal to 0. So we'll work out this root at k is equal to 0. That means at the middle. So as k tends to 0, sine square k tends to k square a square, and hence equation 15 means dispersion relation is written in this way. And here sine square ka was there, and that is replaced with k square a square, and you simplify this one. You go on simplifying this one. That means this m1 plus m2 divided by m1 m2 is taken common here. So that terms, when it goes inside, it is squared and it is inverted. You cancel, and next you take this term from the whole these two terms. You are getting in this way cancellation, and lastly you left with this thing. So actually to simplify this 1 minus k square 4 k square a square divided by m1 plus m2 whole square, this relation is used. 1 minus x raised to half is equal to 1 minus x by 2. This relation I have used. So this is 1 minus that term, and you simplify, cancel, and simplify. We are left with this thing. R omega minus is equal to k into 2 beta dot by m1 plus m2 raised to half. So this is the frequency, angular frequency of the acoustic branch at k is equal to 0. Next, as k tends to 0, omega tends to 0, the atoms are at rest. So by making use of 17, we can obtain the phase velocity and group velocity here at this stage only. The phase velocity Vp is equal to omega minus divided by k. This is equal to a into root of 2 beta out of m plus m2 raised to half. This is v naught. So just now I've just substituted the value of this my omega minus there. This is v naught, and group velocity Vg is equal to d omega minus dk is equal to a into 2 beta out of m plus m2 raised to half is equal to minus is equal to v naught. And for negative root of so these are the this is the values at k is equal to 0. Then for the same negative root of omega minus at k is equal to 5 by 2, what happens we will see. At k is equal to 5 by 2, that means that this is the boundary of the first Boolean zone. I will show it in the diagram. So this is k is equal to 0, and this is k is equal to 5 by 2a, or k is equal to minus 5 by 2a. Same conditions will be there. The boundary or the region bounded by this 5 divided by 2 by ka and minus 2 divided by minus 5 divided by 2a is referred as the first Boolean zone. So you are in the first Boolean zone from here to here. So that is what is called as the zone boundary. K is equal to 5 by 2a refers to the zone boundary of the first billion zone. So, so we are here. So by making use of 17, we can obtain this is over. Uh, so this is simplified, and phase velocity and group velocity both are obtained. And since they are same, it is taken as a V naught and V naught. And for negative root of omega minus at k is equal to 5 by 2a, that is at zone boundary. So at k is equal to 5 divided by 2a, that is at zone boundary, we have what happens to this omega minus. You substitute, and here in place of k was there. For k is equal to 5 divided by 2a, you have to substitute, and a get cancelled. It is sine of 5 by 2. Sine of 5 but is nothing but 90. Sine 90 is 1. So this whole thing becomes 1. So we are left with the 4. And this we have to simplify. So lastly, I am getting omega minus square is equal to 2 beta upon m1 raised to half. This is omega minus. So that means that k is equal to 5 by 2. This omega, this acoustic branch will have the maxima. So this is about acoustical branch. Now I will see the optical branch. What happens to the optical branch at k is equal to 0 and k is equal to 5 by 2a. So the positive root of the dispersion relation is corresponds to the optical branch omega plus. At k is equal to 0, you work out same conditions. For k is equal to only here plus comes, everything is remain same. So sine of 0 is there, so it is 0, and that term goes, this term vanishes, and remaining these two terms you simplify, it becomes 2 beta into m1 plus m2 divided by m1 m2. So that we have to simplify. It becomes omega plus is equal to 2 beta into m1 plus m2 divided by m1 m2 raised to half. So it is clear from the graph that omega plus is maximum at k is equal to 0. At k is equal to 5 by 2a, what happens? That is at zone boundary. Substitute k is equal to 5 by 2a into the equation 18. Sin ka becomes 1, and equation 18 will be like this. Here, because of this plus, this slightly changes. Earlier it was m1, now it is m2. So omega plus becomes 2 beta divided by m2 raised to half. So these are shown in the dispersion relation and diagram also. So this is the angular frequency of the optical branch at the zone boundary. Now we'll see the nature of vibrations in the acoustical and optical branches. So to study the nature of the vibrations in acoustical and optical branches, we will make use of the equation 11. Equation 11 is there, it has came earlier. So it is like this. So you simplify this equation, just you take the RHS and then divide. It becomes zeta by eta is equal to 2 beta minus m2 omega square divided by 2 beta to cos ka. So what happens to this zeta by eta? That is the ratio of amplitude we are working out. So at k is equal to 0, let's see what happens to the acoustical branch. For acoustical branch, this is the angular frequency, and at k is equal to 0, what happens? Here k is there, so this goes 0, and cos k in the denominator cos k is there, that becomes 1. So substitute these two. This is 0 and this is 1, 0 and 1, so it becomes 1. So that means zeta by eta becomes 1. Amplitudes, the ratio of amplitudes is 1. That shows that zeta is equal to eta. So this implies that the amplitudes of both types of the atoms, that is M1 and M2, are equal, and they are independent of masses. That means these amplitudes are independent of masses. These kind of vibrations are generally possible in sound waves, and hence the name acoustic branch. The diatomic lattice vibrate as if it is monoatomic. So that means when this amplitude becomes unity or equal, what happens? This case turns to the case of monoatomic lattice, and whatever that forbidden gap is there in between the acoustic branch and optical branch, that disappears, and hence the case becomes the monoatomic lattice. So diatomic lattice vibrate as if it is a monoatomic lattice. The vibrations are as shown in the figure, or as shown below. So this is the acoustic mode of vibrations of the diatomic lattice. Next, again at k is equal to 0 only, let's see what happens to the optical branch. For optical branch at k is equal to 0, omega plus is given by this equation, and cos k is again 1. Substitute into the ratio of amplitude equation in this equation. So what happens, you see, so it is 2 beta minus m2 into that value you are substituting here, and 2 beta 1. So here m2 m2 get cancelled, and 2 beta is common, 2 beta take it out and it get cancelled. Then you simplify this one, this is m1 minus m1 minus m2 by m1, m1 get cancelled. Lastly we left with zeta by eta is equal to minus m2 by m1. So the ratio of amplitudes is inversely proportional to the ratio of masses. So from this equation it is clear that ratio of amplitudes is inversely proportional to the ratio of masses. And negative sign indicates that the vibrations are out of phase. So here the vibrations of M2 and M1 are out of phase. Earlier they were in phase, now they are out of phase, and this type of vibrations are raised when a crystal such as sodium chloride is excited with an EM wave, means electromagnetic wave. So when an electromagnetic wave or when a light energy is falling on such a type of diatomic lattice, this type of vibrations are possible, and hence it is called as an optical branch. And the oscillations are as shown here in this diagram. So these are the oscillations. So you can see here, this is one type of waves they are going up, and other types of waves are going coming down. And so this is very clear that these two waves are completely out of phase. So thus at k is equal to 0 for optical branch, the two waves are out of phase, and the situation is like this. So this is the complete workout of the diatomic lattice, and it is very important, clearly worked out, and you can work hard, you can make it practice for the examination. Thank you. Thanks for listening.